So in the past, when we've graphed functions, we worked with different types, right? Like linear functions, quadratic functions, and we even hinted towards using cubic functions, right? Well, today we're going to talk about all the higher degree polynomials. So a first degree, a second degree, a third degree, the ones we covered, but also fourth degrees, fifth degrees, etc. So let's just review. If I have y equals x to the exponent 1, that's the parent function for the first degree polynomials. In other words, a linear function, right? Y equals mx plus b, but this is the parent function where your m is 1, there's a 1 on the front, plus 0 is your b, right? So if you're going to graph this, it's just the most basic of those linear functions. It looks something like this, right? It has a y-intercept of 0, a slope of 1, right? So that's your y equals x. Now, you also have y equals x squared, right? This is your quadratic function, parent function. So what does that look like? Well, it's just the horseshoe shape, right? That classic curve like that. Okay, but we also have some other ones, right? We can do a cubic, right? So this one here, I'll say is y equals x cubed. And that does this funny little curve in the middle like that, okay? Then you have y equals x to the 4. Right? If we draw this, I don't think we've taken a look at this one yet, but the parent function, y equals x to the 4, looks kind of like this. So it looks similar to the quadratic function just above it there, right? These look kind of similar in shape. They're both going up on either side, and they both have a sort of vertex here at 0, 0. The x to the 4 just looks a little bit wider, right? And actually, if you look at x to the 1 versus x to the 3, they're also kind of similar in that they start at the bottom left and then they work their way up to the right. It's just that x to the 1 is a straight line and x to the 3 has a little wiggle in the middle, right? So let's continue looking at these. What if we have y equals x to the 5? What do we think that's going to look like? Well, y equals x to the 5 is just going to look like this. Very similar. And it crosses here at 0, 0. It's not quite perfect, but it crosses there in the middle. It looks very similar to y equals x cubed, right? The only exception being that it's a little bit wider, right? It's a little bit more stretched out. And then if you do y equals x to the 6, graph this one, it's going to look something like that. So again, very similar to y equals x to the 4, the one above it, it's just even wider than that. So if you look at all these even number functions, so like x squared, x to the 4, x to the 6, they're all very similar. They just get wider and wider. And the same is true for x to the 1, right? Or I should say the odd number exponents, right? So x to the 1, x3, x to the 5, they're all kind of similar in that they start from the bottom left to the top right. Once you get to this third degree, you have a little wiggle in the middle. And as you get bigger exponents, that gets wider and wider. And that's going to be true. You're going to see that pattern continue for all the odd number exponents. And you're going to see this pattern continue for all the even number exponents. Okay? And again, that's just for your parent functions. All right? Now let's talk a little bit about y equals x cubed, because I already showed you what this looks like, right? I said there's a little wiggle in the middle, goes like this, right? Or that's just a smooth curve. But at the middle here, you can see it's like as you're coming up, you're slowing down, right? Your slope is decreasing until you get to here, because here it's really steep. But then here you're kind of less steep, and then at the middle, you're kind of not doing anything. Your slope's kind of at 0, and then you start picking up speed again. You get steeper and steeper and steeper. So at that 0, at that sort of vertex, you have something interesting going on, right? You have a change in your momentum, if you want to think of it that way. But the reason I point this out is because your parent function is just y equals x cubed, but we could add additional terms to this, right? Like we could have ax cubed plus bx squared plus cx plus d. And the reason I say that is because if you recall from your work with quadratics, if you have y equals x squared, that's just the parent function. But in standard form, you could have a whole bunch of other terms, right? And those are all going to impact your shape with transformations and things like that. Now, for the cubic function, though, all of these terms have the potential to drastically change the shape here, okay? And what I mean by that is at the middle, where you usually just sort of change that momentum, like you're slowing down, and then you start speeding up again. Instead of that change, what you could have is something that looks like this. Again, depending on all these extra terms and the a value here, you could have something that looks like this, where this little change in the middle, where you go up, come back down, and then go up, normally that's all concentrated at this point in the middle. It's all just reduced, but it's all so compacted that you don't really see it, or you can't identify it, right? Because it's not actually happening. But as you introduce these new terms, you can get something like that in the middle. Now, both of these are the same on the ends, right? Like up here, you're going up forever. Over here, you're going up forever. Down here, you're going down and to the left forever. Same with over here. It's just the middle where there's an interesting difference, right? Depending on these things. And so that could be the case. And the same is true for all of these polynomial functions, right? So for a cubic function, you could be going up, back down, and back up like that. But for something like a fourth degree function, so let's say you have y equals ax to the 4 plus bx cubed plus cx squared plus dx plus g. I'll use g for this one. What are we going to have? Well, again, depending on what these coefficients are, you have the potential for a graph that looks something like this. It goes down, back down, and back up, right? As opposed to just if you have y equals x to the 4, where it's just a very wide, like this, right? So in the middle, you have this interesting thing happening, whereas over here, it's just kind of goes down and goes back up, right? So it depends on these additional terms, okay? Because again, on the ends, you have the similar behavior here as you do here. They're both going up. It's just in the middle, around the vertex area, where you have this interesting behavior happening, okay? And this is true for all of these functions, whether it's a fifth degree, a sixth degree, whatever. The trick is knowing how many of these, I guess you could call them waves or bumps, are possible, right? If you look at the last one we did, the y equals x cubed, but the extended one here where you have all these terms, look at how many changes of direction you have, right? You're going up, and then you change direction, and then you're going down, and then you change direction, and then you're going back up. So there's kind of 3 components to this, right? Like 1, 2, 3. Like you're going up here, down here, up there. So those 3 components, you can think of it like, oh, there's 3 of those sections because it's a third degree polynomial, right? Another way people think about this is at most you'll have 1, 2 turning points for a third degree polynomial. So the rule that people come up with is, oh, just 1 less than whatever the degree is. That's how many turning points you can have. And when I say turning points, I'm referring to those maximum or minimums. Really, that's a local maximum and a local minimum, because this here isn't the maximum for the whole graph. It's just the maximum in that area, right, where it's located, right? Because in this area, that's the highest point. And then in this area over here, this is the lowest point. Now, it's not the minimum for the whole graph because this point's lower and this point's higher than that maximum, right? So there is not really a maximum or minimum, but we have a local max and a local min, okay? So you can always remember that the number of turning points will be 1 less than the biggest degree on your polynomial. Again, at maximum, right? Because you might not have something like this. You could have something that just looks like this, right? So this on the left here, this is the most, I guess, complicated version of this graph you could get from a 4th degree. So let's look at some other examples. Let's say we have the 4th degree polynomial still, and let's look at some of the potential scenarios. You could have a 4th degree polynomial that comes down, touches like that, goes up, goes down, and then back up like that. And if you notice, this indicates that you have just one root, right? That's a root, and there's only one of them. But you could also have it go like this. And in this case, you would have 2 roots, right? So it's also possible to have 2 roots for a 4th degree polynomial, right? But you could also have it another way. You could have it look like this. This also has 2 roots, but they're sort of differently placed than these 2 roots up here. So you could also have 2 roots this way. You could also have a function that looks like that. This has no roots, right? When I'm talking about roots, I'm talking about the x-intercepts, right? So you could have 1 root, you could have no roots, you could have 2 roots. What else could you have? I think you could have 3 even, right? Because you could come down like this, go back up, come down, and go like that. So you'd have 1, 2, 3 roots, right? So that's possible. And then in the most extreme case, you would have something like this, and you would have 1, 2, 3, 4 roots, right? So for a fourth degree polynomial, you could have 0, 1, 2, 3, or 4 roots, right? But 4 is the most you can have. And so this is a rule that we're going to keep in mind, is that for any polynomial, the biggest exponent in that polynomial, so if it's like a fourth degree, the most roots you can have is 4. You might have less, but the absolute most you can have is that exponent, okay? So if it's a fifth degree polynomial, the most amount of roots you can have is 5. If it's a sixth degree, the most amount of roots you can have is 6, okay? Now, let's look at some other cases here. Let's say we have y equals mx plus b. This is your equation of a straight line, right? And I'm going to, instead of using m, I'm going to use ax plus b, just to make it look more like, consistent with the other standard forms, right? Usually we have an a on the front of that first variable. And a, if that's positive, or if it's negative, that's going to change the direction of your graph, right? We know about that in this case because if the slope is positive, it means it's going up. And if it's negative, it means it's going down like this, right? But that same trend is true for all different types of polynomials. Like if you have y equals x cubed, that goes like this, because the a value on the front would be positive. But if the a value is negative, it's going to go like this. It's just the opposite shape. It's going down instead. So for all the odd number polynomials, so if it's just y equals x, if it's y equals x cubed, y equals x to the 5, y equals x to the 6, whatever it is, you're going to be going from the bottom to the top if it's positive, or you're going to be going downward if it's negative, right? I can show you some more examples. If we have a graph like this, something like that, that's potentially a cubic function, right? Because it goes up, down, back up. That's a positive cubic function. If you have a function that goes like this, that's a negative cubic function, right? There's a negative a value on the equation. If you have something that goes like this, what type of function is that? Well, you see 1, 2, 3, 4, 5 sort of different sections here. So potentially, this could be a fifth degree polynomial, right? But the important thing to take away is that if it starts in one direction and goes up in the other direction like this, if they're going opposite directions, that means that this is an odd polynomial, right? And because it's ending up going up, that makes it a positive. If you have something like this, 1, 2, 3, 4, 5, 6, 7, that's potentially a seventh degree polynomial. And because it's going down on the right, it's going from up to down overall, that's the general trend, it's going to be a negative. There'll be a negative a value on the front of that function, right? So this would be like y equals negative a x to the 7 plus, dot, 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 all the other components of that function, whatever they are, right? Hopefully that makes sense. Those are the odd ones. If we talk about even functions, or the even exponent functions, like y equals x squared, we're all familiar with this. If it's a positive, it's going to open up like that, right? But if there's a negative on the front, it's going to open down like that. And you might have been taught in school that, oh, positive because it's smiling, it's happy, it's positive. Negative, it looks like a frown. That's fine. I mean, if that's the way you're exposed to it the first time, that's absolutely okay. But this trend is also true for the higher degree polynomials. So y equals x to the 4, that would look more like this. It's a little bit wider. And if it's negative, it goes like this, right? It's not perfectly a square like that, but it's a little bit more exaggerated, right? But you could also have, a fourth degree that looks something like this, right? That would be y equals ax to the 4 plus, all those other terms. And this is a positive, right? The a value would be positive because it's going up on both sides. If you have one that goes like this, what is that? Well, it's going down on both sides, so we know it's negative. In the equation, if you look, there's 1, 2, 3, 4, 5, 6 components to this, right? It's going up here, down here, up here, down here, up here, down here. 6 different sort of sections of this. So I would say that it's probably negative a x to the 6, right? It could be more, right? Because just because something like this is it goes down here and goes up here, that doesn't mean it's just x squared. It could be x to the 4, right? It's just kind of a more simple x to the 4. So it's possible that this here isn't an x to the 6. It could be something higher. We don't know for sure, but the smallest exponent that you would need to make this work is a 6, right? So you need at least a 6 here. So it could be bigger, but at minimum you need that to be an exponent of 6. And we're going to get into more of the details of how to graph these. But for now, I just want to get across the point that if it goes down on both sides, it's negative. If it's going up on both sides, it's positive, right? And for the odd number ones, if it goes up on the right, it's positive. And if it goes down on the right, it means it's negative, right? Really, if you want to know if these things are negative or positive and you don't want to remember specific rules, just look at the right-hand side and see what it's doing, right? Look on the far right. If the far right's going up, it's positive. If the far right is going down, it's negative. Same with these ones. On the far right, if it's going up, it's positive. If it's going down, it's negative. So you can just remember that, and that's usually enough information. Now, let's take a look at how we would start putting these things together. If I have f of x, and let's say they tell me that's equal to x plus 2 times x minus 3 times 2x plus 1. What is this? Well, this is the factored form, right? So in the last couple examples, I've been giving you equations that are in standard form. So like this thing up here, for example, this is in standard form, right? But now we're just being given it in factored form, which is ideal because if something's in factored form, we can go ahead and find the roots, right? You set each of these brackets to 0. So you get x equals negative 2, x equals 3, x equals negative a half. So I just set each bracket to 0 and solve for x the exact same way you would find the roots if you had a quadratic, except now we have 3 brackets instead of 2, right? 3 factors instead of 2 factors. So if you want to graph this, just as a sketch, you'd say, okay, here's negative 2, here's negative a half, here's 3. Those are your roots, 1, 2, 3. And there's 2 ways you can draw this, right? You can draw it like this, or you could draw it like this, right? Because it can only cross at those roots. Now, which way does it look? Well, it's going to look this second way because there's a positive 1 on the front, right? So it's a positive function, so it has to end up going up, right? So see how that goes up? So this is a positive function, so that's how it has to look. Now, how do I know it goes like that and not, maybe it doesn't like bounce off like that or something? How do I know it crosses over? Well, because if you look at this and you were to expand it, your very first term would be x times 2x. That would be 2x cubed. That's your first term, right? I don't care about the rest of the terms. The first term is 2x cubed. It's a third degree polynomial, right? If you were to multiply this out, the biggest exponent would be x to the 3. And so because that's the case, this can only have 1, 2, 3 sort of sections, right? Or 2 turning points, right? Remember, it can only have one less turning point than the exponent. It's a third degree polynomial, so at most it can only have 2 turning points like this, right? So it couldn't go up and then down and then up and then touch a point and come back down because that would have 1, 2, 3 turning points. Wouldn't be allowed, right? So this is how I know what it looks like. We can do another one. I could say f of x equals negative 2, 3x plus 5, x minus 2, x plus 1. And if you were to expand this, your very first term would be negative 2 times 3x times x times x. It's going to be negative 6x cubed. So it's another cubic function, but the a value is negative this time. So when you go and you write down what your roots are, you get x equals negative 5 over 3, x equals 2, x equals negative 1. So you put these down just like that. Those are your roots. And because it's negative on the front, it's got to end up going down. So it's going to go like this, and like this. Right? Also, because it's an odd function, right? Because it's an odd exponent, I should have mentioned this in the last one, but because it's odd, they have to be going in different directions, right? Like up on one side, down on the other side. That's another way or another reason that you know it's not doing something like this, where it just bounces off there, because then it would be going up in both directions and it would look like an even exponent function, right? But it's got to be going in different directions because it's odd. Okay? So that's that. Let's look at another one that's a little bit different. Let's say I have f of x equals x plus 2 squared x minus 3. So you could write this as x plus 2 times x plus 2 times x minus 3, but you don't have to, right? I'm just showing you that's what it's equal to. So you still have these 3 brackets. When you expand it, your first term is going to be x cubed, and then a bunch of other ones. So you can still have up to 3 roots, right? That's still possible, just like the last two. But if you solve for these, factors, you're going to get x equals 3 for this one. And then these two, you get the same thing, right? You just get x equals -2. So it looks like you only have 2 roots now. Well, how is it possible that we only have 2 roots? Well, if you put one at 3 like this, and you put one at -2 like this, how do you do this? Because it's got to be going up here. So is it, well, you can't go like this because that's an even function if it's going up on both sides. So you can't do that. What it's going to look like actually is it's going to come down, it's going to go up, it's going to touch the -2 and bounce off like that. So normally you'd come down, go up, and then back down, and you get 2 roots here, but instead you just have the 1, right? So it comes up a little bit early, just touches the x-axis at a point and goes back down. The way you know that this is happening is because this x plus 2, the factor that represents this root, is being squared, okay? If you have an even exponent on a factor, or if the factor shows up twice like this, what we say is that that's an order 2, or you might hear the phrase multiplicity of 2. If you have an even number multiplicity or an even number order, that means you're just going to bounce off, right? It means you're going to bounce off the x-axis. You're not going to cross. But like over here, x minus 3 only appeared once, right? It's just to the exponent 1. So that means that it's an odd number multiplicity or an order of 1, right? Meaning that it's going to cross instead of bounce off, right? So based on how many times that factor appears, you can determine what the behavior is at those roots, whether it's just touching or if it's crossing, okay? Let's do another one. Let's say you have f of x equals x minus 4 times x plus 3 squared. Well, this first one here, you have an order of 1, or a multiplicity of 1, because it just appears once, right? And that's x equals 4. So because it's an odd order, that means it's going to cross at that point. This one here is an order 2, or a multiplicity of 2, because it's squared, right? It's appearing twice. So the root is x equals -3, but because it's an even order, or an even multiplicity, it's going to just bounce or touch the x-axis, right? It's not going to cross it. So when you graph this, we say, okay, here's 4, here's -3, those are your 2 roots. It's positive because there's a positive 1 on the front. If you multiplied all this out, the first term would be x cubed, right? So you'd be going up here, go down, you touch at -3, and you go back down. Okay? Let's look at another one. And for this one, we'll have a couple different orders. So we'll do f of x equals x plus 1, x minus 3 squared, x plus 2 cubed. So for this one here, you can see there's an order of 1, so it's going to cross, and that's at x equals -1. Here, you have an order of 2, meaning it's going to bounce, because that's an even number, and that's at x equals 3. And then here, you have an order of 3, so that's an odd number, so it's going to cross, and it's at x equals -2. Now, let's take a look at what this looks like. So you have -2, -1, and 3. Those are your roots. What would be the very first term here? Well, you'd have x times x squared times x cubed, so it would be x to the 6 would be your first term. So it is positive, and it's going up on both sides, so it should finish looking like that. Now, we said it's going to cross at -1, and it's going to cross at -2, right? And then at 3, it's going to bounce. So if it bounces at 3, that means it's coming down and going up like this. And then at -1, it's going to cross, so it's just going to go down like this. And then at -2, it's going to cross, but the order is 3, not 1. So when it crosses, it's going to do a special kind of cross where it does a little squiggle like that. That's not the best, but imagine what's happening here is when you have a y equals x to the 3, you know how it does that shape? Or I should draw that the other way actually, but you get the idea, right? You know how it goes like this? When you have y equals x cubed, it does that little squiggle. It's that same squiggle here because that factor, because that root is represented by the factor something cubed, right? Order 3. So when it crosses, it's going to do a little squiggle like that, okay? So that's important to note. And that's what your graph is going to look like, okay? Let's do one more. let's say we have f of x equals negative 3 x plus 4 x plus 2 squared x minus 1 cubed times x minus 2 to the 5. If you were to multiply all this together, your very first term would be what? Well, you have an x to the 5, an x to the 3, an x to the 2, and an x. So 5, 6, 7, 8, 9, 10, 11, negative 3. So you get negative 3x to the 11. So I'm just adding up the exponents on the x's times negative 3. And you get negative 3x to the 11, and then a bunch of other terms. So it's an odd function, right? It's an odd exponent polynomial, and there's a negative on the front. So it's going to end up going down. It's going to start by going up, right? So on either end, it's going to look like this, and then something's happening in the middle. Now, what about all these factors here? What about all the roots? Well, here, you have an order of 1, so it's going to cross at x equals negative 4. Here, you're going to bounce, because it's to the 2, at x equals negative 2. Here, you're going to cross, but it's a special sort of wiggle the way you cross because it's cubed, not to the 1. And that's going to be at x equals positive 1. And then here, you're going to cross as well because it's to the exponent 5, which is odd, but it's going to do a similar wiggle that the cubic one did, although it'll be a little bit wider and more exaggerated, just like how the y equals x to the 5 looks, and that'll be at x equals 2. So let me show you what I mean. We're going to write down all these roots. So you have negative 4, negative 2, 1, and 2. Now it's negative, so it should be going down over here. It's going to cross at 2, and remember what I said, 5th degree, so it's going to be sort of an exaggerated wiggle like that, sort of like that. It's going to cross at 1, and it's going to do the same thing, so you got to fit this in like that, so it does another little wiggle there. And then it's going to bounce at negative 2, so it's going to come up to negative 2 and bounce off like that. And then it's going to cross at negative 4 just the way things normally do. So it's just going to go like that. All right, it all fits together, right? It's negative, odd, so it starts up here and ends down here. So it looks like we did that correctly, right? Doesn't look like we made any mistakes. It looks like that's actually pretty good. Okay, and so that's all you got to do. Now, the next video, what we're going to do is show how to get this factored form if it's given to you first in standard form, right? Because if it's in factored form, this is easy, right? Or maybe not easy, but you look at each root, you find out what they all are. You go ahead and you say what it's doing at each root, whether it's crossing or just touching, right? And then you sketch it together, right? It's not too bad. It takes 1 page, just like this. But if it's in standard form first, how in the world do you factor it to get like this, right? Because we know how to factor, trinomials, but can you factor something that has 4 terms or 5 terms or 6 terms or 7 terms? What do we do? That's going to be in the next video, so check that out.